talk today from Liu Huimin about bug finding and exploit techniques for file transfer apps on Android phones. So if you have your file transfer apps open at DEF CON, really? But if so, this might be a good time to turn it off. This is Liu's first time speaking at DEF CON, although he has given talks at CanSec West, Black Hat 8, basically all over the world he's given this. So give him a welcome, and we're going to give him a classic DEF CON welcome with the speaker shots. Cheers.
Thank you. Good morning, everyone. My name is Liu Huimin, and Zhang Xiangqian is my colleague, but he won't come here because of some visa issues. So I will do this talk alone. Yeah. Now we will present you a comprehensive research about exploits of nearby file transfer apps. The title is "Your Secret File Are Mine," and bug finding and exploit techniques on all transfer apps of all top Android phones. First, let's introduce ourselves briefly. We are from Advanced Technology Research Team of Tencent Security Xuanwu Lab. Tencent is the largest social media and entertainment company in China. And we focus on mobile security and IoT security, and we found many Android kernel and system security vulnerabilities and accomplished many fancy attacks. And we have presented many slides like this. This is our presentation outline. First, we will give an introduction about the nearby sharing technologies and talk about our motivation to do this talk. Secondly, we will present the attack surfaces and some previous work. Next, we will show you the real vulnerabilities and the exploit and the demos. Next, we will show you the real, then we will talk about the mitigation method. Finally, it will be our conclusion. Now, let's begin our part 1, introduction. There are many nearby transmission technologies such as Bluetooth, Android Beam, Wi-Fi Direct, but we focused our research on nearby sharing apps on Android, including smartphone vendors' built-in apps and third-party developers' apps. Many users want nearby file sharing apps. Why? We believe that Bluetooth and Android Beam based on NFC have two weaknesses. First, not user-friendly enough, and secondly, not fast enough. When you want to share a picture to your friend, it usually takes seconds or minutes to transfer a big picture. But this technology based on Wi-Fi technology will be transferred fastly. When we want to send or receive a Blu-ray movie, it will be not capable at all. So nearby transfer apps that are based on Wi-Fi related technology are people's new choice. Based on our research, we found that nearly all top smartphone vendors have their sharing apps. So based on the IDC's data, we can find that the shipment last year is nearly 1 billion phones. 1 billion within a single year. That's a big number. If they are vulnerable, a huge number of people will be affected. So we began our research. This is what the Android sharing apps look like. It is a little like the AirDrop on the iOS and iPhone. That there are several ways to connect and send files on Android. In this example, when both sides are of active status, the sender just selects a file and the receiver will be shown on the screen, and then the receiver can tap the profile picture of the receiver, and the receiver will click the accept, just like the airdrop. Then the file will be transferred. Some apps use another approach. The receiver clicks the receive button, and then the sender can see the receiver, and they establish the link and accomplish the file transferring. There are little difference here, but there are many differences in the security design. There are some other ways, such as scanning the QR code to transfer files, or shake the phones at the same time. On the other hand, many nearby file sharing apps will show the thumbnail. This will introduce a new attack vector. We will detail it later. Yeah. The sharing process or nearby sharing apps are shown here. In general, there are 4 steps. First, discover by BLE advertising name, ID device type, and so on. Secondly, we can pair. So most apps pair and exchange keys automatically, which is very convenient, but it is vulnerable. Thirdly, connect via Wi-Fi or Wi-Fi P2P. Finally, we can transfer files such as pictures, APKs, and so on. Since we know the general sharing process, let's analyze the attack surfaces. First, the adversary are nearby. The attackers can be sniff and sender or Bluetooth and Wi-Fi packets. Then, what the attackers can eventually get when attack succeeded. First, the attacker can get the transfer files and more, such as hijack the traffic, getting more information, and even remote code execution. Here, the attack surfaces are as follows: link establishing, secure transmission, device and ID spoofing, man in the middle, and others. First, when link is establishing, automatically, attackers may join to a network without users' permission. On the other hand, attackers may obtain the established network password because of unsecure connection. When files are transferring, there may be no encryption at all, so we can get the file directly. And sometimes, the key exchanges are not safe, so attackers can recover all the real file from the encrypted traffic. Next, device and ID spoofing. Many apps fail to authenticate the real device or users. For example, when Alice wants to send a Bob a file, then the attacker can collect all the Bob's advertised information and advertise themselves to create a fake Bob. In this case, many apps fail to distinguish between the fake and the real Bob. We call it device and ID spoofing. Based on the device spoofing, the attackers may accomplish the man-in-the-middle attack, so the normal user will feel nothing. We'll show the demo later, but the technical details will be explained later too. What's more, we found some other interesting attack surfaces. For example, some sharing apps will start a web server, which will open more doors for attackers. And there are other information disclosure we can't even think about it. And Android components related attack surfaces. We are not the first researchers to notice the nearby communication apps. When researching about the zero conf on OS 10 and iOS, researcher Bai Xiaolong, etc., analyzed the airdrop and found some vulnerabilities. And on NDS 19, some researchers reversed analyzed the Google Nearby Connection API. However, there are nothing about file sharing apps on Android. My colleague and I will present this on this talk. To the best of our knowledge, our research is the first comprehensive research about Android nearby sharing apps. We analyzed many related apps, include pre-installed and third-party apps, and we found a lot of vulnerabilities in these apps. and then we arrange them in several common attack methods. Here, let's show you some of the real vulnerabilities. Notice that in this talk, we will focus on the specific, we won't focus on specific apps or vendors. So I will cover all the vendors and the apps name here for security. Yeah. Besides, there are huge number of users will be affected. I will cover all the critical code too. Yeah. Some of the vulnerabilities are not fixed here, so. We will present 4 vulnerabilities categories. Sniffer attack related vulnerabilities. 2, the middle attack related vulnerabilities. Then we will talk about logic vulnerabilities. Finally, we will present all the other vulnerabilities here. First, let's talk about sniff attack. This is a built-in app or smartphone, and we will take it as our example. These 3 pictures show the normal file sharing process. The receiver don't need to input any password or something else. Yeah. The whole process is totally automatic. However, more convenience can often mean less security. This app uses Bluetooth Low Energy to advertise and discover other peers and transfer files by Wi-Fi P2P. Can it accomplish a secure key exchange here? To capture Bluetooth data, we can use a Bluetooth sniffer such as Ubertooth, NRF51, and so on. This is a BLE packet we captured. It is a scan response packet, which is sent when some other device are scanning. It contains user ID, device name, and some other information, such as some flags and spotted cipher versions. The packet is an advertising packet, which is often easy to understand. And this is a BLE data packet. The BLE sends data in 37, 38, 39 channels, but Ubertooth can only sniff 1 channel at a time. So we need to sniff several times to get the data packet. The picture shows the encrypted data transfer when establishing connection between different versions of apps. So we extracted the data here and it looks like this. What does it mean? The answer lies in the app itself. So we reverse engineering app. This is a core crypto algorithm. We can see that it is obfuscated badly. But we managed to recover a function which mainly rely on AES crypto and some other transformation of data. To make it more clear, we can show you an older version which is different but without any obfuscation. But the whole process is just the same. In this older version, there are nothing but an AES encryption which was different from the new version. But the overall logic was still the same. Yeah. So the P2P info is P2P info you can see in the slide is the encrypted information. And the P2P CFGEX here is a plain text decryption by calling decrypt function. And the key was generated by the function generate secure key and generate root key. This picture shows the decrypt function, which we can see the AX decryption here. Yeah. To decrypt the data, we need to get the AES encryption keys, which rely on the source string array and the M secure random. A secure string array can be gotten from the BLE packet. What about the M secure random? Its name contains random. However, we think that it must not be the random number because the sender and the receiver must have the same number of this. So we found that it was stored in some XML file and it is fixed. That's interesting here. So now the whole encryption can be break and we can recover data directly. This is a decrypt process for the older version of the app. The latest version was far more complicated, but we managed to reverse engineer it. But it is similar in the design. We break it too, and we will show you the output. The upper image shows the recovered P2P info old version. The second image here shows the recovered P2P info new latest version, so we can see the SSID and password are gotten by us. So everything they transferred will be get directly by us. Based on the recovered password, we can join the network and get the transferred files through ARP spoofing. And let's show you two demos. Here, a right phone take a picture. And then he will send the picture to the left phone. And the computer acts as an attacker. So we can see the info that were collected there. Then the left phone got a notification, and then when he click the accept here, we can see that the computer will get it too. And this is a full photo. We just take a picture of that. Yeah. Here is demo 2. It is the process is a little different, but there are some more interesting here. Something very interesting, I think. The left phone wants to share a picture to the right phone, and we can see that the picture was gotten by us. You can see the pop-out on the computer. We checked it's the latest version when we recorded the video. And when transfer apps, actually, this is a picture, yeah. And this shows what all the apps you installed on your phone. When sharing apps want to sharing a photo here, he will send all the apps you installed on your phone to the other phone. It's a terrible info leak here, I think. Next, let's move on to the second category, man-in-the-middle attack-related vulnerability. In nearby sharing apps, when the senders want to select a receiver, he can see profile picture, device name, user ID, and so on. Our question is, how can you authenticate that it is a real one? We found that it is very tricky. In this slide, we can see that we can emulate a receiver by using a BLE scan standard app to send advertising and scan response packets. The left phone shows a profile picture of someone, but it is actually a BLE standard app. Yeah. Then the receiver will be shown on the standard screen. And in this picture, we modify a real device to spoof another device. There are two active receivers here, but the senders can only see one device. So when he wants to send a file, he will never know which device it will be sent to. Now, we can spoof another real device. Then the attacker can accomplish perfect man-in-the-middle attack when emulated a fake receiver and a fake sender. As we can see here, if A sends B a file, there will be 50% chance that the file will be sent to the attacker, and the chances can be improved by many ways. Now, a perfect man-in-the-middle attack can be designed like this. A can find the attacker because the attacker will not send a scan response to A by our design. B can find the attacker because B is not in discovery mode. Then the attacker can distinguish between A and fake A, B and fake B, because he can choose to block or receive any message. So the normal user A and B can feel anything. This is a demo. We didn't implement the whole process or the main in the middle here due to time limitation. In this demo, we just verify that the sender can distinguish between the real and fake receiver. So our main in the middle attack will work properly. Here we can see the normal user send the file, and sometimes the normal user get the file, and sometimes the attackers will get the file. So here, the attacker will get the file here. Oh, yeah. Now let's go to the third category, logic vulnerabilities. First, let's think about a question. How to design a secure process to establish connection between sender A and the receiver B? We think it should be like this. User A request to send and B accept, and then the link will be established. Then A sends the file and B will receive it successfully. But actually, most nearby sharing apps will establish the Wi-Fi connection as soon as the sender A just sends the request. But why the app developers choose an unsecure way? We think that they might have their own consideration here. More clicks often means less convenience, so the developers don't want their users to double confirm. And the receiver often want to see a thumbnail about the file to decide whether accept the file or not. So convenience wins and sometimes security loses. Firstly, the non-confirmed connection brings more attack surface here, and the attackers can now establish the Wi-Fi or Wi-Fi P2P connection without any interaction. It will open doors for attacks to exploit other vulnerabilities and even achieve zero-click attack here. Just exploit the file image protocol, yeah. Secondly, we can hijack the victim's network. In these two cases shown on this slide, we can see that when transfer files, that one device creates a Wi-Fi hotspot and the other device connect to it directly. However, it is not this easy to hijack network successfully. First, if attackers want to hijack the network, they must be the hotspot server. Can we choose to be a server? We found that we can. For some apps, the senders are definitely the server creator. It is okay, because here we attackers are always senders. For many other apps, we found that when an app running on Android 7 and another app running on Android 8 want to establish a connection, Android 7 is always the server because some compatibility issues here. Secondly, we will make the other user to connect my Wi-Fi without interaction. Can we do that? We found yes, because it was designed like this. Yeah. Let's show the demo here. The victim just check his internet access and he just opened the file transfer apps and just leave it here or make it in background or turn it off. turn the screen off here. The attacker requests to send him file. And then when victims open his browser, and he'll be hijacked. Yeah. Finally, it's our fourth category, other vulnerabilities. We will share 3 examples here. 1. Accept automatically via Wi-Fi P2P. 2. Directory traversal. And 3. Remote file management vulnerabilities. In this case, when sharing files, this app will establish a Wi-Fi P2P connection. We can see that when other devices want to join them, it will need to provide the correct password. However, when we use Wi-Fi P2P protocol to directly connect it, we found that anyone can join them without any confirmation here. And the normal users won't feel anything, so we'll get the file directly. This is a second logic vulnerability example, and in this case, it is a directory traversal vulnerability. The file transfer was accomplished by web server. So the senders may create a web server and send the receiver a URL to get. Then the receiver can modify it to get any files here. Let's show the demo here. The right phone is the sender. Then he got a secret image. But he wants to send another normal image to the left phone. But here, the left phone will get anything he wants. And in this case, we will share a file management related vulnerabilities. If an app wants to open the FTP server, computer within the same local area network can manage the file in smartphone. We found that many apps didn't have any authentication here and secure design. Any users have read and write permissions here. So if the attackers are in the same lens, they can get and read all your files here. This is a summary of vulnerabilities in nearby sharing apps. First, non-confirm before Wi-Fi connection established. 2. Not well protected access to Wi-Fi or Wi-Fi P2P. 3. Unsecure transport. And finally, no anti-spoofing at all. Those vulnerabilities patterns affect nearly all the nearby sharing apps. We finished our 4 common vulnerability categories, and now we present you our security survey about nearby sharing apps. The red X means no security measures at all. The yellow O means have security measures but can be bypassed here. There are no one green here, but I will show no brand here. There are little security measures such as access control when Wi-Fi was established here. Then we did a security survey for top 10 third-party nearby sharing apps. And the results are shown here. Most of them are vulnerable too. Only 20% of them can prevent sniffer attack, and only 10% of them can prevent spoofing. And notice that this is the test results on Android 8. If we test them on Android 7 or lower, nearly all of them will be vulnerable because Android allows the app to create a hotspot with their self-defined password on Android 7. So when Android 7 and Android 8 make a connection, the Android 7 will always be the server and will be vulnerable. Yeah. finally, let's talk about the mitigation. This is our 4 advices about mitigations. Sorry. First, we need more secure Wi-Fi and Wi-Fi P2P key exchange. And 2, we need transport encryption. And 3, it must designed to prevent spoofing. And finally, there are other small tips. First, the app must have secure Wi-Fi and Wi-Fi P2P key exchange. So we recommend that the app transfer the key over secure channels such as NFC, certificate-based key exchange mechanism, and the internet. On the other hand, the PIN code is a good choice too. Now, nearly all apps transfer files without any transport layer encryption. When we recommended that the app use TLS HTTPS instead of TCP HTTP and transferring keys over the internet securely or pre-exchange keys for contacts. It is not very easy to prevent spoofing. We prevent a method here, we present here, but we use the certificate-based authentication. When the app launches for the first time, it will get a unique ID distributed by the server and corresponding certificates signed with predefined trust anchor. So attacker can't sign the unique ID correctly. We can make sure that the device can distinguish between the real user and the attackers. There are some other tips. First, we must prevent attackers from joining the network and stay file sharing turned off by default and turned off them and after a period of idle time. And confirm before connection established. And finally, do not establish connection automatically with users who are not familiar. This is our recommended design. When users are logged in, we recommended pre-exchange public keys and authenticate automatically for contacts, and exchange keys through the server when there are internet access for other peers. When users are not logged in or have no internet access at all, we recommended PIN code, NFC to exchange keys. PBC and DV-Human here is easy to deploy and have some security measures here, but it is not very recommended because it can prevent man-in-the-middle attack. Now, this is our conclusion. We analyzed the attack vectors of nearby sharing apps and did the first comprehensive research about them. And we found many vulnerabilities here, and we categorized in several common attack methods. And finally, we present some effective mitigation methods here. Thank you. Now the mitigations will be deployed on many apps here, but we can't tell which app is secure because the vendor didn't want to say that. Sorry about that.